All right, recording is on. Okay, so sorry about the delay. I'll try to finish this in 1 hour. Actually, today I was hoping to sprint till the end, but I guess we shouldn't rush this. So we'll see how far we go. If we don't finish all the slides today, we can always finish it tomorrow. So let's, as usual, recap where we were, what we did yesterday. Yesterday, we looked at a few simple, we looked at basically what VTGate does, converts, what VTGate does to convert from the SQL to the AST to the final relational tree or opcode tree that it plans to, that it will eventually execute. So there are a few things that I might have forgotten to mention yesterday. One is, as you can see here, we are actually pushing actual AST data structure elements into these routes. And obviously, this is not the final plan. So which means that there is a final phase where these AST elements, this AST tree under each route becomes an SQL, which means that there is actually a parallel data structure for joins and routes. So there's one set of data structures that we use for building the plan, and there's another set of data structures that we use for executing. So that is one comment. The other comment is compared to a traditional relational engine, where the AST elements are converted to relational operators, and then the optimization is performed purely on the relational operators. Here we are actually cheating. We are actually analyzing operations in the AST elements and interpreting them as relational operators. So that that sometimes confuses people because the traditional mind wants to convert it to first the relational representation and perform optimizations there. So in our case, we are actually, it's as if we are actually running an interpreter on the SQL AST and interpreting each of those constructs on the fly as actual operators. So that's the way I would draw the parallel. We actually do the conversion to the actual operator only when we determine that we cannot push that construct down into one of the routes. So that's a slight difference that often confuses people. So I just wanted to mention that. All right, so now let's actually, any questions from yesterday?
Nope, all set.
All set, okay. So let's start the presentation. So we are back to where we were yesterday. We have the same AST tree that we analyzed. And we have now built the two routes, both for A and B. And but now what we are going to do is we are going to see how the symbol table grows along with as we perform the same operations that we did yesterday. So the first thing that happens is when I created, when I encountered this symbol table, this symbol called A, and actually, let me try and see. It happens actually when A gets pushed into the route. There is a symbol table that is built for route 0. And it contains one symbol A. In terms of pointer, the symbol A does not point to anything, but the route, hold on. The symbol points to the route. Basically, the symbol A says, I am defined in route 0. And the route 0 actually points back to the symbol table, not the symbol, saying that the symbol table that has my symbols is in this table. Make sense? And as you can see, B also has the same story, and they currently don't know about each other. They live in separate worlds. And when the recursive algorithm actually finishes A and finishes B and comes and looks at the join, is when these two data structures meet. And at that time, what happens is the two symbol tables are merged into one. And A continues to point to R0, B continues to point to R1, but R0 and R1 actually point to the combined symbol table that contains A and B. So far, so good. And then after this, there is nothing new because all we are doing, we are not creating any new symbols, but we are actually resolving. Every time we look at a symbol, we actually, this is basically what tells us where to push each element, right? So when we looked at A dot n equal to B dot n, what we are actually doing is, where is A dot n defined? A dot n is defined in A, and that is pointing to route 0. B dot n is defined in B, and that's pointing to route 1, and therefore we have to push to route 1. So that's basically how we are concluding that A dot n equal to B dot n should go to route 1. So that was kind of voodoo science yesterday when I explained saying that find the rightmost route. And this is basically the data structures that we use to identify the rightmost route for each of the constructs.
So, sorry, Sugu.
Yeah.
So it's rightmost in what sense? It's rightmost like as the child of the join, or it's rightmost in the merged symbol table, or maybe both?
It's a rightmost route.
Uh-huh.
The reason why it is the route is because today only routes can contain AST elements, right? So we have to push this into the rightmost route.
Right. So I'm asking, in what sense is the route rightmost?
Oh, the route is rightmost from the order in which the query was defined, which is basically it was select from A join B. So A is on the left and B is on the right.
Okay, thanks.
Yeah,
and, and sorry for the background noise here. I'm in a Starbucks.
Oh, I don't. It's fine. I don't hear much noise here, so we're good. So basically, the one assumption that I guess I didn't cover is that VTGate does not try to reorder the joins. It always joins in the order in which the query is specified. Maybe one of these days we can look at reordering the joins for better optimization. But right now, it doesn't have enough information to do any kind of smart ordering. So it assumes that the application specified the tables in the best join order. So from that perspective, if you have a join order of A, B, and C, then A will be the leftmost and C will be the rightmost. And the order in which we walk the tree is representative of, is the same order in which the tables are specified in the select statement. And therefore, the left to right order that you see in the join clause is also the same order that you would see here. That makes sense?
Yep, thanks.
And as these routes come together, they get renumbered. So basically, the rightmost route is basically the route with the highest number. So if you went to A dot n equal to B dot n, you say, oh, where is A dot n? A is here, that is 0. B dot n is 1. Therefore, we go to route 1. And when we go to A dot id equal to 5, then it only references A, and that ends up being route 0. That's the highest route. Therefore, that's where the where clause has to be pushed. All right. So that's so A dot id equal to 5 ends up with route 0. and this condition ends up in route 1. And we continue. Nothing changes here, except that we still continue to use the rightmost route rule by resolving each of these symbols against a symbol table, and it tells us the route number, and we always push it to the highest route number. And when we are pushing, we don't worry about external symbols, because we are going to resolve them at a later time. And now the magic happens, which is as soon as I'm done analyzing the select, there is a whole bunch of new symbols that have cropped up in this table. Currently, these are A and B are called tab sims, which are called table symbols, and the top ones are called col sims, which stand for column symbols. Like I said, we don't know the schema, so when we see something like a.id, we implicitly assume that A must have a column named ID, and therefore we are going to honor it. And that's how we actually do the pushdown rules. And that's the reason why symbols A and B, which are actually tables, don't have a column list, because there's no point maintaining a column list, because anyway, we don't know what it is. I mean, we could build a tentative column list based on the constructs we see used in the query, but that doesn't really add any value for us. So we might as well not worry about building a column list for each of these tables based on the select that we see.
Sugu,
Yeah.
are table tab sims always coming from pre-select, and then column sims are always coming from just the select part?
Correct. Tables always come from clauses.
Okay.
I think there is one. I might have seen one other construct where a table is used in something other than a from clause. And in any case, I don't think we have that in our grammar. So
Okay.
if we ever end up adding that, then we have to make sure that we can handle it here.
Thanks.
And that actually is a very, very important fact to remember, because that basically tells us that while we are analyzing other parts of a select query, we know that we will not add to that list of tables. So once we are out of the from clause, we will not add to the list of tables anymore, because any other reference to a table inside any of those other constructs would have to be in a subquery. And if it's a subquery, the story is different. So here, actually, you can see that the call sims has two symbols. One is the unqualified name. The other is the qualified name. The qualified name is currently up for debate. I initially had the qualified name when I used to enforce the rule that post-processing constructs are not allowed to reference the underlying table. So if you had a group by, it was or an order by, it was only allowed to reference the call sims and not the tab sims. But now that the rule has changed, we have to actually wonder if there is value in actually building a qualified name for it, because it's really not necessary, because if you use a.id in your order by clause, it will resolve to the table, and therefore there will be no error. But we have to look at all the use cases. So I'm just mentioning that here. And what else? So far,
Sorry, Sugu. I mean, don't you need the qualified name? I mean, if there's an a.id or some other non sharding key sounding thing, the a.a1 and there's a b.a1, for example. Or whatever, like an a.name and a b.name.
They will all resolve because of the fact that there is a table named A underneath, or a table named B underneath.
Yeah.
So they will resolve successfully.
Sure, but then, I mean, it seems like we need to keep the qualified name around in the call sim so that we can resolve the symbol for these group by, order by parts, right?
Well, that's the thing, right? What if you actually did not want to use a call sim? So we don't really, we don't enforce that a group by references a call sim, right?
Okay.
So we say that a group by is allowed to reference a call sim or a tab sim. And so if you referenced a.id, and it may be in the call sim, but it will still get resolved as a.id because of the fact that we now can see table A inside the symbol table. There is still the requirement, the smartness that we may have to add, where we say, oh, this column is already in the call sim, and therefore we don't have to add it additionally to my list, right? In order to do additional processing. But that's a different matter. Does that make sense?
Yeah. Okay. Thanks.
Yeah. So at this point, we don't really care. So the time when it may become relevant is actually it may be. Here's an example. Right here, there's an example. Right. Actually, not a.n, but let's say we are in a post-processing construct, and there's a reference to a.n there, right? And that post-processing construct, let's say it goes to route 1. In that case, it will reference the underlying A inside the symbol table, but it is not present in the select list. If we did that, if we did that, it will still be fine because the wire up process can figure out that that symbol is not in the select list and will add it. So the wire up process is already smart enough to do that. So if you add reference to a.id and it resolves to the table, and then later you want to see that a.id is already being selected, the wire up process does look for symbols already selected by the select list, and it doesn't duplicate them. Does it make sense? I guess that was kind of what your question was, right? What if the column is already in the select list, but if we resolve it against the table, will we end up not optimizing our query correctly?
Yeah.
Yeah. So I think the wire up process is smart enough to know that, to resolve the fact that they are the same thing. And we will actually, I'll go through the data structure. When we go through the data structure, it will be obvious. Actually, every one of these call sims has a field called the underlying representation, which actually points to the table from which the column came. So if the underlying representation and the reference actually are the same, then we don't actually add it to the add another item to the select list.
I may have missed this. It looks like call sim is attached to R0. Should it be attached to the rightmost or?
Which one? Oh, the call sim.
The entire.
Oh, the
entire
call sim. This is, I didn't want too many lines crisscrossing with each other. This is just an example that says that A1 is attached to R0.
Oh, okay, gotcha.
There are many lines missing here because if I drew all the lines, this would be too confusing.
That makes sense.
Yeah, and actually at the end I have a more formal presentation of the data model. There you will be able to see the different relationships. They are basically named. Here it's just a kind of a approximate sketch of what's going on. So B.B1, ideally there should be a line from there going into R1, and there should be a line going from ID to R0. So I think that these aliases can be deleted, and if we delete it, I think V3 will still behave correctly. But the best thing to do is to just delete it and see if anything breaks. And I don't think anything will break. But it is the current implementation does maintain these aliases. Sounds good? What else is there? There are actually another set of lines that are not shown here, which is that each of these symbols actually points to these elements, like a.id, the AST data structure that's representing a.id is actually pointing to A. B.n is actually pointing to B. This a.id is actually pointing to the colsim. A.a1 is pointing to this colsim. So there are actually way more pointers than you see here. And how those pointers are built is when you actually call the symbol table and say, find me this, this reference, the symbol table, as soon as it finds the reference, it actually updates the column identifier that I sent in and puts a hidden pointer in there. So that is the only place where I cheated in SQL parser. If you look at call ident, you will see a field called metadata. And that's a blind interface. Basically, it can contain anything. And this is where we use it, where the symbol table, when it resolves a call identifier, it actually puts a pointer in there that points to either a tab sim or a call sim. And the reason will become obvious later. The reason is because if I don't have the pointer, what happens is that because the symbol table evolves over time, the question that a symbol table answers today will not be the same as what it will answer later, right? So when only A and B were there, it would have resolved something to the tab sim. But once the call sims are present and you ask something to be resolved, it resolves to the call sim. However, if you go back to an old item that was previously resolved that had yielded a tab sim, and you asked it, oh, resolve it now, it may actually resolve it to a call sim. So for the resolution to be repeatable, these pointers have to be saved into the original elements. And so when you ask, when you take the symbol and say resolve it again, what the symbol table will do is, was the symbol previously resolved from a call before? If it was, then it actually returns the reference to that. So in this particular case, what this means is that if I have an a.id here, because it was initially resolved using A, I ask it again, it will not now find the a.id in the call sim, for example. It will say, it's still resolved to the tab sim that's in A. Make sense?
Yeah, that makes sense to me. I don't know why that's the behavior that you want.
The reason why we want that behavior is if these pointers change, if the meaning of these pointers change over time, this becomes very dangerous when subqueries come into play and scoping rules come into play. And when you are splitting these ASTs into smaller parts, and then you are trying to say, oh, okay, I have an external reference, I need to go find where it's coming from. It may accidentally resolve to something that the original query would not resolve to. You see what I'm saying?
Yeah, thanks. I was getting those scoping rules, but wanted to make sure. Cool, thanks.
Yeah. So once it is resolved, we basically hold a hard-coded reference to that symbol so that we can always find that symbol when we want it. Otherwise, a query that looks one way in the original representation may actually do something completely different when we split it up into smaller parts. So this is one thing that this is one reason why people are uncomfortable with manipulating ASTs and interpreting ASTs, because this danger doesn't exist if you actually were in a purely relational data structure. Because in a purely relational data structures, we don't have symbol references. We only have pointers to actual items. So there is no fear of resolving to something incorrectly. So this is actually the only special handling that I had to write to protect ourselves from the fact that we are actually manipulating AST elements directly. And we have to make sure that the meaning of how symbols are resolved don't change over time. Okay. And this is where external symbols are resolved using the same question, which is when now that I've built the tree, and now I'm going to say, okay, I'm going to do the stitch up phase, the wire up phase. And then I go and ask, I basically walk each tree, and I start with the rightmost and go to the left. I don't think there is a necessity, but that seems natural because rightmost depends on the left, so you should start from the right to left. So I go to R1 and go to its AST, and then walk the entire tree and ask each symbol, are you local? So I ask B, are you local? And say B says, okay, where am I? And this symbol is R1. I'm currently on R1. Yes, I'm local. But when you go to A.N, it will say A.N is A goes to R0. R0 is not R1. I'm not local. So A.N needs to be obtained from outside. So that kicks in the algorithm, the wire up algorithm. So which means that now we know that we are in R1, A is in R0. So we say, okay, who is the common joint between us? So we go to the common joint between us and say, join, please provide A.N to the right-hand side and fetch it from the left. And so that's so join then says, okay, add A.N to the select list. So this wire up phase is smart. It knows that A.N is not referenced in the call sim, therefore it adds it. If the join was on A.A1, then it would not have added it. It would have reused the existing select from here. And then it says, okay, here is the bind variable, and now we rename A.N to colon A underscore N. So the stitch up is also performed by asking the symbol table a simple question, am I local? If I'm not local, then we procure it. Cool. Now comes the nightmare. What time is it? Okay, let's see how far we can go. So now it's all fine. Everything is fine, right? This is actually kind of quite straightforward. You can explain this in English and people can understand. This is intuitively understandable. But what if a subquery is somewhere? And the thing about subqueries is they can be anywhere in your query. You can have a subquery inside a join. Basically, you can select from a subquery. You can say equal to subquery. You can put a subquery in your select list. You can put subqueries in your having clause. I don't know if group bys allow, but who knows? Maybe they will. Order by, maybe. But definitely having, it doesn't really make sense to allow subqueries in group by, order by, and limit. But mathematically, I assume it's allowed. Actually, it may not be allowed because a group by references actual elements, and a subquery is an expression, so therefore it may not work. But definitely having, select, where clause, and on clauses can have subqueries.
I mean, MySQL has some like this information schema. So actually, I can imagine some nightmare scenario where you actually have a subquery over this other thing, and like pull out where the value of this thing is the name of a column. But I think you're right. I think it's got the wrong type. It's not.
Yeah,
at that point, it's an expression that happens to have the same value as a column name.
Yeah, Fortunately, SQL is not Python, where you can build a property out of a name.
Yes, thanks. Yeah, thank God for that. We have one small mercy here.
Yes. So, what is the challenge with subqueries? The challenge with subqueries is that when we are analyzing this particular thing, this entire thing could be a subquery, right? That's the problem. So if this entire thing was a subquery, how would we analyze this? And how would this subquery interact with the outer query is basically the question. So that's the question we have to answer. And in order to answer that question, what we can think about is, what are the things that we can do with a subquery? In terms of like if there is a subquery inside a join, what can VTGate do with it? Is the question you could ask. Or if it was in this equality, can VTGate do anything about it? The simple answer right now is VTGate is not going to do anything about these subqueries right now. But one thing that VTGate can do is, if the outer query has a target route, if the outer query goes to route A, and the subquery also goes to route A. In other words, if the outer query and the subquery have the same target route, then I have a very simple answer, which is make the subquery part of the outer query and send it as pass-through. So the one important question that we have to answer is the subquery an individual single route? Is question number one. And question number two, if so, is the subquery, is the individual route of the subquery the same as the individual route of the outer query? Is what we have to answer. Actually, it's not even individual route of the outer query. Is there a route in the outer query that matches what the subquery has, right? Because if there is A join B join C, and if there is a subquery that has the same route as the one that B has, we can actually send the subquery as part of that B expression. Right? So that is one thing we can do. And what would be the rules that we would use to make that conclusion? The rules we would use is, if it is unsharded, if the subquery goes to an unsharded database and the outer query goes to the same unsharded database, brain dead conclusion, no problem, merge the two and send the subquery through. If the outer query has has a unique index value, like ID equal to 5, and subquery also has ID equal to 5, then also it's pretty straightforward. Both the subquery and the outer query can actually go together as part of the same query. There is a third case, which the best way to describe it is, if the subquery is correlated, but the correlation is on a unique index column. Basically, the rule that we applied for joins, where if a join condition was on a unique index for both, and they were both on the same index, then the fact that the two join expressions could go into the same route, that same rule applies to subqueries also. Like I said before, relationally, from an operational perspective, evaluating a subquery is similar to what you would do for a join, which means that every time you get a row and then you execute a subquery. So if the subquery is restricted by a column value that's a unique index that is coming from the outer query, then that actually tells us that the subquery can also go into that the subquery can actually be executed along with the outer query. So far, so good. Okay.
So do we ever fan out? So what I'm saying is that the if the outer has a scatter route, and we see that the subquery, like we could actually just put it against. I guess this is the case of the correlated subquery.
Yep.
Do we ever also? Yeah. Okay. So we could then.
It's the same rule as the join rule. So if the subquery is correlated, is a dependent on the same column index, right? Then the scatter will still work. The time when it will not work is if the correlation is not on a unique column index, right? Then basically, in order to fetch a row from the dependent rows of the subquery actually are not in the current shard. Then you cannot push the subquery down.
All right, makes sense. Thanks.
So the other thing we can do, which we can reserve ourselves for the future, is that if a subquery cannot be merged to the outer query, we need to have at least a game plan. That, well, if a subquery does not merge to the outer query, what do we do about it, right? Then there's actually, so this is actually not code that is not there in V3, but we can add it later. I actually have a sample pull request that shows how to do this, but we haven't merged it because it was just a proof of concept. The way a subquery, there are a few ways we can treat a subquery. Like if a subquery is correlated, then the mechanism we go through for a nested loop join, that same mechanism can be used, which means that you have the query as one route, the subquery as another route, except that what joins them together is actually not a join operator, but a special operator that does what you have to do for a subquery. And like I said, if you're going to start dealing with subqueries, there are 5 different operators that you have to support, 5 different conversions that you have to support. One is value conversion, column conversion, row conversion, table conversion, and there's a row plus column conversion. So you need to support those conversion operators, and you have to also support the arithmetic operators that the subquery can be involved in, for at least in this case, for example, equality. But you could have plus expression, minus expression. So all those things will be needed when you want to support subqueries in other forms. But for now, the only thing that VTGate supports is it looks at a subquery and says, can I merge this with the outer query? If so, yes, let's go ahead. So that is the high-level strategy for handling subqueries. The more specific question is, what do we do? Do we write special code for handling subqueries? The problem with writing special code, if you have something like, if it is a subquery, then do something else. Then we have actually a problem, because then what if that subquery had another subquery? So the design constraint that I added was the code that analyzes the main query has to be the same code that analyzes a subquery. In other words, when we analyze a query, we actually don't know whether it is actually the outermost query or whether it's actually a subquery. Whatever analysis we perform has to work equally well for both. That sounds great, but we still have to worry about the fact that when I'm analyzing a subquery, and now I've encountered a subquery, I'm actually in a certain state in my code, right? I may be actually down inside analyzing an expression, and then I encounter a subquery. So what that means is that the analysis of a subquery should not depend on the state the outer query is in. In other words, I'm halfway done analyzing my outer query, and then I encounter a subquery, and then I call into the subquery and say, analyze this subquery. That analysis has to fully complete, which means that the subquery analysis will have to go through the entire process of analysis. In other words, if I say I'm analyzing a where clause, I cannot say I will only go to the extent of analyzing the where clause of a subquery because I haven't progressed beyond the where clause in the outer query. You see what I'm saying?
And is it the case that the scoping rules of SQL support that?
Correct.
Yeah. Okay.
They actually no. It's in other words, the way I would answer that question is the scoping rules of SQL still apply to each subentity, which means that if I'm in a where clause state in the outer query, but the subquery has a having clause, when there is a symbol reference inside that subquery that tries to reference something in the outer query, then the where clause constraints have to be applied. That's basically what the constraint is.
Mm-hmm.
So that is the main challenge. So the code actually had to be written in a very specific way to be able to analyze a subquery completely while the outer query was still in a half analyzed state, basically. And what does that mean? That also means that when I go into analyzing a subquery, the route of my outer query has to have been decided, right? Because if I don't know the outer query's route, then a subquery cannot merge with the outer query. So that is one problem. The other problem I mentioned is the resolution of symbols in a subquery. If a subquery has an external reference, we cannot immediately convert it to bind variables. The reason is because after analysis, a subquery can merge into its outer query, and if it does, what was initially an external symbol now suddenly is not one. Right. So if a subquery referenced a.n from the outer query, and if we did the stitch up as we built these routes, and then at the end of the analysis, I come out and say, oh, this subquery can be merged. And if I had actually rewritten that a.n to be using a bind variable, now my subquery is broken. I cannot merge the subquery. And that is the reason why we do the wire up as a second phase after the entire tree has been built. Because after the entire tree has been built, routes are not going to change, nothing is going to merge. Then we can be certain that what is external is actually external, and we can then replace those into bind variables. Sounds good? Here is a subquery example. So this is the same query as we have been analyzing, except that it has an additional AND condition, which is a.call in a subquery. And the subquery does a select. It's a simple subquery. It has a route. And as you can see, it says c.id is equal to b.id. There's a twist in here. So what that means is that this subquery will have the same route as what b eventually ends up in. That's basically the intent of this example. So I think this I've covered, needs to be fully analyzed. Some decisions of a subquery have to be postponed, especially the external variable reference. And this is the third problem, which is the symbols of a subquery need to point to the outer route if it merges with the outer route. So I think I will explain this later when it will be easier to explain that problem when we have pictures. So we are starting again. It's again the same problem, except that we just have a subquery. So in this case, because we are in the where clause, the only symbols that we have built here so far are A and B, right? The call sims don't exist here because we are at this point only analyzing the where clause. The call sims exist only after we finish analyzing the select clause, which means that the subquery can only see A and B. So if in your subquery you had referenced an alias or a count star or whatever, here you would basically get an error from MySQL saying, oh, you can't do that. Does that make sense? So you'll actually see in my unit tests that I often use the having clause and put subqueries in there. That is basically to test if the subquery's external reference can resolve to symbols in the select clause, because having clause is allowed to reference them. So here is a subquery. So like I said, when we go into a subquery, we are not, we kind of set aside the outer query and we analyze the subquery as if it is on its own. We analyze as if it's on its own, but we know that it could have an outer query, which means that when we resolve symbols, a symbol can escape out of the subquery. A subquery symbol table is a different symbol table than the outer query symbol table. And the subquery has a parent points to the outer query symbol table, which means that if a symbol is not found in the subquery, then that symbol is sent to the outer query, and it goes on until it is either found or not found. So in this case, when we analyze the subquery, we build C, we build C.call. When B.id was encountered, it will have asked this symbol table, where are you? So I'm not here, and it found it in the outer symbol table. And here I have actually shown the pointer, and B.id resolves to the B that's in the outer query. But when this happens, this subquery, this symbol table remembers that B.id was actually an external reference. So it remembers that because we are going to use that. What are we going to use that for? So once we have finished analyzing a subquery, we are going to treat it exactly like a normal expression, which means that we are going to apply the rightmost rule to it and then push it down wherever it can go. The only constraint is that because the subquery has a from clause and because the subquery has a route, the routes have to match. And the second thing is, if the subquery had external references, of those, the rightmost reference is used to decide which route it corresponds to. So in this case, when we saw, the subquery referenced B.id, so its rightmost route is R1. And then we say, okay, is R1's route same as the subquery's route? Of course it is, because it's B.id equal to C.id. So it is a dependent subquery on a unique Windex column. Therefore, that subquery can directly be pushed into R1. As you can see, this is actually a complex query. Oh, there's a line missing here. This is actually a complex join, and we can still push subqueries down to smaller parts. As long as the rules, the constraints are compatible, we can still push the subquery into individual routes. If the subquery itself was a join, we give up. We say, sorry, we can't do anything. I actually brainstormed ways whether we can push one part of the subquery to one route and another part into another route. That kind of, I kind of almost lost my head there. So there is one final problem. The final problem is that here is the problem. C.id refers to C. and C points to the route that was built for the subquery. Right? That's what we saw here, right? C.id points to C, and C points to R0. So when we merge the subquery into the outer query, the R0 is still there, right? The C is still pointing to R0. That now is defunct because we just threw away that route because the subquery merged into the outer query. We have a few ways to solve that problem. The way I chose to solve it is to actually mark that route as defunct and point it to R1. So when you ask C.id what route do you belong to, it will go here pointer chasing, it will go to C, it will go to R0, and R0 says, oh, I don't exist anymore, and then it will go to R1. And so when you are doing external symbol resolution, and when you are walking down this tree and you're looking at C.id, it will resolve to R1 and say C.id is local, you do not have to fetch it from somewhere else. So what that means is that if the subquery had made references to A, those would be automatically converted as bind variables, and all the right thing would happen, just like it would have happened on a normal query. Sounds good? This is actually the most complex part of my presentation. If you understand.
Yeah, that was pretty complicated.
Just for the record, it took me a month to figure all this out. I think I spent a month just thinking about this. So if you don't get it on the first attempt, it's okay. But this is the easiest way I can present the facts for you. All right. So basically, but from a from a pure user perspective, it's kind of straightforward. Basically, if there is a query and there is a subquery, VTGate tries everything it can to piggyback that subquery with some query fragment that has its own route. And that's basically what VTGate tries to do. The specific example that I worked on as a subquery is actually an in clause. So if you had a select where a.call in, actually this very construct, which is a.call in subquery. So that's what I have a proof of concept for. And you can see it on my branch if you're curious about how I did that. Thing. Finally, this is a conclusion. This is actually the real data model. This should contain all the lines that we have. So let's go item by item. Where shall we begin? Let's start with the primitive and route, right? So the redirect is, I can cover the redirect immediately. The redirect happens when a subquery merges with an outer query and the route loses its identity because it has merged with the other one. And the reason why that redirect happens is because if this redirect wasn't there, I would actually have to chase down all the symbols in the symbol table and repoint them to the original route, right? So that's basically what I wanted to avoid. I just wanted to add this one level of indirection. As they say in computer science, everything can be solved by adding one additional level of indirection. So the route can be redirect to another route. If it's a join primitive, the join can point to a left or right, and a join can point to a join also. It doesn't have to be a route, which means that you can cascade joins. So that is this relationship. Primitive a route points to the current. What does it point to? AST. Oh yes, a route contains an AST because the AST is the query that is being built for that route. So that is this green arrow. A route will point to its current symbol table. Just to clarify here, multiple routes can point to the same symbol table, especially. So basically, when a route points to a symbol table, the symbol table has multiple symbols, and some of the symbols could point to other routes. So this is a case where you have a join performed by VTGate, where there are multiple routes. They all point to the same symbol table. A symbol table represents one select statement without its subqueries. So that's the reason why, but a route can only point to one symbol table because a route is part of one query. And if we go inside the AST, obviously AST nodes point to each other. That's how ASTs are. That's why it's called AST. Node has a special pointer, which is the column reference. This can be either a call sim or a tab sim. A symbol table contains symbols that can be call sims or tab sims. Every symbol points to a route because right now only routes define symbols. A symbol could point to its underlying implementation. This is if it's a call sim, I say, oh, by the way, I'm a pure representation of this table column, which is used for optimizations. And the symbol also knows the symbol table that it's part of. And this relationship is used to determine whether an external reference belongs to the current symbol table. So, so when b.id has to be, when I come out of this query and then try to find the rightmost route, this symbol tells me all its external references. And so I need to find the rightmost route. But it is possible that I myself am a subquery, right? Which means that some of these external references here may not actually belong to this query. So that's the reason why when I search for symbols and a symbol is found, I verify that that symbol indeed is part of this symbol table, and therefore it can be used as candidate to identify the rightmost route. I know you didn't understand that, but you can listen to it later and it'll make sense. It'll all make sense when you go through it again. Okay, so this is the last of the slides. And we are just about out of time. So tomorrow we can go through the code. So the way I would say it is, if you understood everything up to subqueries, that is kind of good enough for you to get into the code. The only time you will need to go to handle the complexity of a subquery is if you have to actually deal with improve plans that deal with subqueries. Otherwise, you can kind of stay away from that part. The only influence that the subquery has is how the thing is designed. But otherwise, if you understand the design as it stands, without knowing why, then that is good enough for you to change, to make changes to the code. So tomorrow we will actually do an actual code walkthrough. I don't know if we can finish it in 1 hour, but I'll try to. If we finish, then we are done. Otherwise, we may hold one more session. The other thing I've been meaning to add, I'll probably add it to these slides. That is to cover the specific example that Alex was going to work on, which is how do we handle unions? If we have to add support for unions here, what do we need to do to make that happen? So we can cover that part just as an exercise. And then we can have him do the implementation. Cool.
Sounds good.
Yep, sounds good. Thank you.
Cool. All right. I will see you again tomorrow, same time.